Hello, everyone, and welcome to Burt Process Equipment's educational webinar on pump transfer stations and pH neutralization systems. I'm Mark Turgenti, the Director of Design Engineering for Burt Process Equipment, and I want to thank everyone for joining us today. With me is Madison Mulqueen. She'll be helping facilitate the questions, and Bill Elliott, who will be moderating, and there'll be a few poll questions that will be posted throughout the broadcast. We will have time for questions at the end. Should anybody have any questions throughout, please feel free to put them into the chat window, the questions window, and we will get to them at the end of the broadcast. Anything we don't get to, at the end of the broadcast, we will send out emails. There will be a follow-up email to this that we're always interested in your feedback on things we can do better, as well as ideas for future content. And with that, let's get started. What we're going to really do today, we're going to do kind of a sort of a high-level survey of talking about both pump transportation as well as pH neutralization systems, and really how the two of them very often are tied together. And when I talk about lift stations or transfer stations in this case, what I'm really referring to is those which are really tied into like chemical and like laboratory waste drain lines. We're not going to talk today about like sanitary waste style pump transfer stations. We're going to focus more on the chemical side and how they're integrated into pH neutralization systems. So for those who are unfamiliar, pH neutralization system is a process system which is installed really on the final drainage of any laboratory or healthcare, semiconductor, pharmaceutical, food and beverage, different institutional research laboratories, even in some larger high schools where people are utilizing some kind of chemicals, whether you have an acid base, you have laboratory, you have wet process chemistry. This is a system that monitors, treats, and then allows for safe discharge of waste into the sanitary sewer system to allow you to be discharging your waste in spec. And kind of the ideal range for pH, that's mostly defined, and it does vary from region to region, really falls in kind of the 6 to 9 pH range. As you can kind of see here, pH really kind of runs the gamut, 0 being acidic, 14 being basic, and 7 being neutral. And there's a lot of different things that we utilize on a daily basis that are actually kind of out of that range. And obviously, from your house, you don't really care. You're talking about things are diluted out. But when you're talking about an actual process facility of some type like I just described, you do need to account for where that waste is going to fall and allow it to be neutralized and discharged safely. And really the primary takeaway from looking at the pH scales, understand that pH is logarithmic by nature. So every step that you move away from neutral, you're going up in relative strength of orders of magnitude. So, obviously going from, 6 to 7 is 10, 100, 1,000, so on. So you have a pH 2 waste stream versus a pH 3 waste stream. You are considerably more acidic in those cases than you would be, as compared to if you were on a different part of the pH scale. And there are two kind of sort of super categories of pH systems. There's the active system, and then this was referred to as a passive system. We're going to talk about active systems today because that's obviously the more modern technology. Some people probably do know passive systems. That's what I refer to as the old limestone chip tank design. And while they're still used in some very niche applications, most systems today are active pH adjustment systems, which monitor the pH in real time as part of the treatment system and allow for the, basically two-way adjustment across the entire pH scale under controlled injection of either an acid or a caustic injection. As I kind of alluded to earlier, the typical pH range tends to fall somewhere in the 6 to 9, 5 to 8, 5 to 10 pH range as governed by different municipalities across the country. There are three primary types of pH neutralization systems. There's the flow-through system, the batch treatment system, and then there's the hybrid flow-through batch system. A flow-through system is what most people who understand these systems commonly associate. And in the flow-through style system, waste comes into your reaction tank or series of tanks, is treated, and then allows to kind of flow out of the system in a steady state. And you're treating it based on what's referred to as residency time, either across one or multiple tanks. A batch style system allows you to have waste come into your system, You hold it for a certain amount of time, you shut off your effluent, and you allow it to treat to completion. Batch systems are much more flow dependent, obviously, because you have to actually shut off the flow coming into and out of your system while you do your batch. But they do have the benefit of never allowing you to go out of spec with your waste. They're commonly associated with very high strength or specialty wastewater treatment, such if you have pH in the range of say 1, less than 1, or greater than 13, or if you're doing other types of treatment in addition to pH, such as if you're doing fluoride treatment or having fluid decontamination, all referred to as biokill going on in your system. Batch style systems are fairly common in those cases. And then you have what's referred to as the hybrid flow batch system, which kind of combines really combines aspects of both of these systems, whereby under normal operations, I operate the system as a flow through style design. And when I need to, I go into a temporary batch mode by shutting off the effluents and allowing there to be buildup in the tank while the influent is still in operation. And that's done either by residency volume in the tank, or having an out-of-spec tank, or having an equalization tank as part of your actual system. The major components of a pH neutralization system are the treatment tanks, agitation, chemical injection, and controls. As I mentioned to you before, you kind of see here a couple different examples. Of each one of these, you have your treatment system here. It's a 3D rendering. This is a two-stage system. And in a typical flow-through design or even a hybrid style design, this is what's referred to as having more than one stage as part of your system. And each of these stages is based on the industry standard residency time of about 20 to 30 minutes, depending upon the relative strength of your waste. And this is achieved by what's referred to as creating a CSTR, or continuously stirred tank reactor, as part of your treatment system, as well as the agitation that goes along with it. And here's your agitators, which are located here. The typical agitation rate as part of a system is approximately 2 tank turnovers per minute. And as your waste comes in and you monitor your pH and your chemicals are injected, you can basically achieve what's referred to as a well-mixed solution, which allows you to move the pH effectively about 2.5 to 3 pH units per stage. A little more custom designed. You can see here you have like a 4-stage system. This is typically done based on room allowance. This is your typical chemical injection, which is achieved through chemical dosing and metering pumps. So as I mentioned, you can see here, this is a pH neutralization. Residency time, 20 to 30 minutes. There are actually some DEP codes that actually dictate what they want for residency time. For example, if you're operating in New York City, they want a 15-minute residency time as a minimum, but 20 to 30 is typically the standard in these cases. Most treatment tanks are going to be some kind of a thermoplastic material, but they're going to be polypropylene, rarely polyethylene in very small situations. Fiberglass potentially have very large applications. If you're doing a system which can be rated to a much higher flow rate, you may end up with a fiberglass tank design, as well as stainless steel potentially, although again polypropylene is by far and away the most common, which you kind of see here in this case. Taking a look inside the tank, you kind of see the cutaway here. This is what I was referring to a moment ago. You have your waste which comes in and flows down right into your mixer backwash here. Not shown, but this is your chemical injection ports which follow down. So essentially you're putting in your chemistry right where you actually have your waste coming in directly into the mixer backwash in this case. That allows you not, and what that allows you to do is not what's referred to as short circuiting your tank. When you short circuit your tank, what that means is the waste comes in and goes right out the effluent. It basically is not mixing the solution. It basically cuts right across the top of your system. And that's really done by kind of looking in here. You can see an actual picture of one. By having that sort of downpipe and then having that properly design agitation. I'm not going to go in too much today into how agitators operate, and the sizing of them. But as a rough calculation, as I said before, about 1.5 to 2 tank turnovers per minute is fairly common for doing agitation in a pH neutralization vessel. Systems are typically controls, is what's referred to as tempered proportional control. And what that means is you're basically proportionally, as you measure your pH as part of your treatment tank or series of tanks, you're basically proportionally matching your chemical injection of your acid and base reagents to match the pH curve. So what that means is if you're out around pH, say 3 or 2, or getting further away from neutral, you're running at a very high flow, and then you gradually turn it down proportionally until you get very close to neutral in those cases. And typical set points are about 6 to 8, with a target of 7 in the middle here. And this is predominantly done through their PLC control. Some people still use local pH transmitters as it means to actually do what you can see here. This is a full PLC display, which actually shows the two tanks as well as how you do that level of proportional control as part of your system. So this is what I was describing earlier. This is essentially how you would proportionally turn down your caustic and acid pump injection. And the two most common forms of chemical injection, two most common chemicals used for reagents are 50% sulfuric acid and 25% caustic. There's a lot of variation. It's just important to kind of know up front what kind of chemicals you want to use in your system as a means to allow for chemical compatibility as well as having that proper control. Reagents in the system, whether they're going to come in a drum or whether you're going to use them as part of your reagent, what reagent tanks need to be 110% double contained. You can see in the video here, that's actually what a pH probe looks like. pH probes are effectively a consumable of the system. pH probes have a certain lifespan. It's just how they're designed with their double junction, how they actually measure the pH effectively. And they are a maintenance item. They do need to be cleaned, as you can see there, as well as calibrated. And they can go in a number of different ways. It can be an insertion style pH probe, which goes into the top, which is what this example is. It can also be ones that go in through like a ball valve on an actual pressurized line if you have, say, a recirculation loop as part of your system. And there's a lot of different pH probe selection designs out there, as well as different ones that are designed for better applications, some for high purity water, some for HF environments, some that are based, some that have, some that have actual cleaning apparatuses associated with them. Because obviously you can have all these large tanks, mixers, but obviously what's really the linchpin of the whole system is really keeping that pH probe in operation. I can't tell you how many times I got into a facility and I've seen them pull them out and they're covered with stuff and they have to be cleaned, and then the pH probe will change by a matter of 5, readings effectively. So it's important to have that as part of your system. One of the things I didn't really talk about before was, when I was talking about residency time in the system, talking about the different treatment tanks, and we're going to talk a little bit more about how you actually do a flow profile. And how you actually calculate that, as it relates to having pumped versus gravity flow systems. But as part of an actual pH system, we talk about CSTR. And residency time. Residency time is effectively the flow rate divided by the tank volume. And the tank volume is set by whatever your maximum instantaneous flow rate is through your system, which can be hard to determine. But you need to look at that based on what you believe the instantaneous flow rate could be. Not looking at the averages or kind of a low end, because obviously it's during those high flow peaks where you're going to end up with the potential to have an out of spec condition. Now, before we go to the next slide, I think we're going to do one of our first poll question. Again, these are totally optional. We're going to talk about it at the end here as well. Yeah, about 30 seconds. All right, so the first poll question, what treatment tank sizing is based on which of the following flow rates? As we were just kind of talking about here, average flow, daily flow, max instantaneous flow, 25% more than the max flow. Really, two of these could be right. Really, the correct answer is C in this case, which is the max instantaneous flow. While you could potentially oversize your system for more as a case for future expansion, that's not typically the norm with these style systems. And again, solving for your average flow rate is difficult because, as we look at talking about a flow profile, you could end up with, flow of say 100 GPM for 10 minutes and then no flow for an hour, and you're gonna come up with an average flow rate of say 10 gallons a minute, which is obviously just not the case. So it's important to actually have that, and there are ways to also control that. So if you do have that kind of situation where you have a very high flow rate coming into your system, but only temporarily, then there's certainly an option in there to equalize that flow rate upstream of it. A little bit about kind of what a pH system is, and really what we're trying to do today is kind of build from what it is, what are the components, and now talk a little bit about how you kind of design these. We'll go to case studies, lift station, and kind of sort of really kind of tie it all together. It's great to say, okay, I need 2 tanks, or I need a hybrid, I need a batch, but how do you really get there? And that really depends on understanding what the nature of your waste is. And this is kind of its own conversation, but sort of touching a little bit on it here. There's a number of things you can look at. Obviously, if you're looking at, a particular type of facility, you have a chemical list, you know what you're putting down the drain in those cases. And that can really drive you to, this is what you want to do, as far as I'm always going to have the same pH as pH2 waste coming into my system. More than likely, though, you're going to have a number of different processes, a number of different potential labs, scrubbers, tools, and you're going to have a lot of variation in your waste. And that's part of the reason why that kind of CSDR model applies. And you have things like residency times that you can really catch that pH swings that are going on in your system, but also kind of helps drive home the point. Are we talking about very strong waste streams most of the time, or are we talking about very weak waste streams? A college lab for biology, for example, is not going to have the same relative strength as, say, a semiconductor fab, as an example. And it's kind of important to look at what industry you're in as well, because that'll really kind of help point, do I have HF present? Am I just talking about some cleaning chemicals? Am I a pharmaceutical or beverage manufacturer? It's going to be flushing caustic down the drain constantly as they basically scrub kettles out with Wi-Fi water. These are the kind of things that we look at. We really determine what kind of system makes the most sense in addition to the flow profile, for your system. So I do want to highlight one of these things here, which kind of comes up. It comes up occasionally, and that has to do with alkalinity. And alkalinity comes into play when we're talking about, we have a stream that has a lot of high purity water in it. So high purity water, whether it's Wi-Fi water or ultra pure water, pH is alkalinity is essentially a measure of the buffering capability of a solution. So basically, it's your ability to actually affect the pH of it. And there's two ways to kind of flip the coin. You can have very low alkalinity, you can have very high alkalinity. More often than not, you always refer to as very low alkalinity. In a low alkalinity stream, such as a high purity water, you get much more rapid changes in pH than you typically would if you were treating this as part of a normal system, where you would have standard water, for example, you get a fairly linear curve, as I was showing you guys before on the kind of P&ID slope. When you have high purity water, you have very rapid changes, kind of illustrated here on this diagram, where you're kind of jumping up and down effectively. And what you really want to do, and this is done by adding a buffering chemical to your system, is get kind of a nice smooth line of treatment, a very linear curve that's basically proportional as you basically move closer to your pH targets. It's hard to say how often this is going to come up, and it comes up in very specific applications, but it is one of the things that kind of catch people off guard, for example, and they go put a system on, they sized it right, they have the right chemistry, and all of a sudden they're going to just see these massive oscillations. It's because you have too much high purity water going through your system, and it needs to be addressed to have that proper level of control. So how do we look at a flow profile? And as I said before, you're talking about a pH system which is going to be on really the drainage line of an entire building, or entire lab space, or multiple labs, or it could be multiple tenants. If it's a tenants, they're going to have different lab spaces. And we do this in a lot of different ways. One way is obviously looking at what you have for lab sinks. Obviously, you have your lab sink or fume hood, which can have a cup sink in there, ties into that. That could be dishwashers, autoclaves, semiconductor tools, clean room environments, vivariums. And you're looking at saying these are not all going to dump at the same time. If you ever walk around a lab or industrial space, you walk by a lab, half the things are sitting there idle. We look at all these different examples and we assign a flow rate to them, and then we assign a diversity factor to them. The other thing that often happens is the bigger you make a facility or you add on to a facility or change it, you simply can't get from point A to point B without pumping it. It may not be possible. This is part of the lab risers, where the flow is going underground, for example, out of your building, to then be able to get to a pH neutralization system. And that's where lift stations come in. And you can see here, these are some of the different flows: slab sinks, cup sinks, and fumes. And we'll come back to this here in a few minutes. But what is a lift station? A pump lift station or transfer station is kind of two different terms for really the same thing. Is effectively what it sounds like. It's basically a place where you're connecting the gravity line, and you are then repressurizing and pumping your waste to a different place in the building. And you can see here, it's a very simple. You have a tank, some kind of level monitoring or multiple level monitoring, and you have a series of pumps which then allow you to transfer the waste in these cases. And looking at it from a P&ID standpoint here, you have obviously very small lift stations. They're obviously quite a bit bigger, stainless steel kind of lift stations here. These really depend on a number of different factors. Lift stations, they're made out of very similar materials to what you're going to do, what you're going to make. The pH system out of thermoplastics, potentially stainless steel in these cases. The relative process complexity is not as complicated as a pH system. Obviously, this is really just designed to transfer waste in those cases. But there is a lot of nuances into how these types of systems are built. And some of the simplest ones are very basic kind of simplex style lift stations. A simplex lift station can be the size of your laptop, effectively a 12 by 12 by 12 box. When it's open, goes into a lab, goes under a sink, part of a chase. Could go next to a single tool, for example, and has a single pump on there. And these are very often designed for applications where you don't need redundancy or you can't fit it in the space. It could be a single point, it could be a single fixture that's easily taken offline for maintenance should the pump fail. And obviously, it tends to be on the lower flow side of things because it's only servicing a very small area. Again, most of these tend to be fairly small volume and fairly small flow, or you're going to basically go with what's called a simplex design. Most people go with duplex lift stations. And the reason you do this is if you're bringing all this waste you have as part of your drainage system into a pump design, you want that level of redundancy. If one of your pumps fails for whatever reason or clogs, if you don't have a secondary pump, your only option is to overflow your system at that point. Even with a pH system, which a lot of them are gravity, if you have something goes wrong, it just kind of keeps on flowing effectively. With a pH system, you have a single point of failure, which is going to be your pump in those cases, which is why duplex, I would say, is 80% of the time what you're going to be utilizing. Duplex is a critical process, these large numbers of things, an entire building, entire lab floor. In rarely situations, you also see triplex designs. Now, that being said, waste lift stations like this are not designed the same way as like a booster pump pack, where you have, say, the flow is split on a 30-30, 40 split or something like that. Each of these pumps is usually designed for the full flow rate. So they operate in lead lag. So if one pump fails, the other one kicks on at the same flow rate. And they also operate alternatingly, so that you can alternate between different pumps, between the pumps with each cycle to kind of minimize wear on the pumps. Burt Process does offer a number of standard design lift stations, ranging in a fairly typical range from about zero to about 80 gallons a minute, and tank volumes from 7 gallons, which are ones designed to go say into like a lab chase, into like a lab sink, to 260 gallons, which can then support sort of, it's like a small industrial or multi-lab building. And these all use corrosion-resistant CPVC, polypropylene, or PVDF vertical style pumps. That being said, lift stations come in a lot of different shapes and sizes. And kind of the reason I sort of show this is there's a couple things to know about lift stations, but kind of the nuances come into it. One, It's not just a tank and a pump in these cases. Depending on where your gravity line comes in, this may have to go into a vault space. You may have lower inverts coming in, so you end up with pumps that need to be able to draw to the bottom, or you need a self-priming design. You may have different chemicals that could have hazardous, i.e., like explosive chemicals, such as solvents that, well, we aren't going to go to the pH system. They go to like more of a solvent collection, and you have explosion-proof design lift stations. If your flow rates are really high, you're going to be outside of a 260-gallon tank. So you have a 250 GPM or 300 GPM flow. You have a residency time of a lift station that could be 1,000 or 1,500, really scaling kind of up from there. Some of the lift stations that I've worked on have been 2,000 or 3,000 gallons, for example, or up to 15,000 gallons if you're supporting a large enough flow potentially coming into it. Lift stations aren't necessarily designed based on a residency time like a pH system, like a CSDR. They are designed more on, um, you know, basically not short cycling the pumps. So if you have a pump that, peristaltic pump that can run dry, you can make the station very small in those cases. But typically 3 to 5 minutes is fairly consistent to basically minimize pump cycling. But it does depend. There's a lot of different pump styles. You can see here, stainless steel cell primers, the bearing pumps, the AOD pumps that can be utilized as part of a lift station. Again, specific to what you're pumping, and again, what your flow rate is coming into your system. Another example here, this is just a lab-based design. They have a large tank here, and then they have a pump skid as an example. Again, this all kind of falls under the umbrella of a lift station. Where that changes in the tank volume becomes very important is if you're utilizing it as more of an equalization tank, such as in the kind of the case here, whereby you want to actually, as I gave that example earlier, if I have, say, 10 GPM coming into if I have that 100 GPM for 10 minutes coming, and that's all the flow I have for an hour, I can collect that 1,000 gallons and then pump it out at like a 10 gallons a minute effectively. It's still a lift station, but it's also an equalization tank in those cases. Um, Again, this is like the cell priming design. These are line tanks, obviously for more high strength chemicals, fiberglass for high temperature. If you have things like steam condensate, for example, coming into as part of your drainage system. The other options, if you do, which I don't recommend, have to bury the tank to the rim. You cannot do it out of thermoplastic. You have to do it out of fiberglass or metal. You do not direct bury chemical lift stations. A lot of that falls under the fact that while people do make direct bury fiberglass tanks all the time for, say, water or gasoline, they're actually UL tested specifically for that application. And putting in kind of a chemical mixture into a tank underground, there's a lot of insurance and a lot of listing issues that kind of come up with whether or not you can do that and some of the parameters that come into it. So 90% of the time, lift stations are put in vaults, or something, and they're actually accessible as part of their actual design. At this point, we're going to do our second poll question, and we'll have it open for about 30 seconds, and then we'll kind of do a little discussion on it. All right. So when should you utilize a duplex lift station? When redundancy is important, when you have critical process, when downtime or backing up a system is important, and obviously it's all of these different reasons. And as I said before, 80% of lift stations will be done duplex. The only reason to go with simplex isn't really necessarily even a cost. It's more of a practicality. It's a very small design. It's only servicing something very simple in those cases. Otherwise, having that level of redundancy is very important as part of kind of a critical structure there. So how does this all tie together? So lift stations and pH systems, I'm going to walk you guys through a little bit of a case study here. And we're kind of talking about 480 lab sinks, 5 glass washers, and 10 autoclaves. As I said before, each lab sink is 1 GPM. The glass washers will define the cage washers. And what's important to look at now is when I have split flow. So I have flow here that needs to be pumped. It can't get to the actual area by gravity. And I have some which it can then flow by gravity. So I need to design a lift station as part of my overall design. So when talking about a lift station, one lab sink 1 GPM times 20 GPM, two cage washers at 16 GPM. I have a total pump flow of 36 GPM. For a lift station, you do not apply diversity. You're going to pump it basically at its 100% flow rate because you have to at that point. When you're talking about a gravity feed into a pH system, you can apply that diversity for a lift station. If you do end up with a bit more of a spike, you don't have that CSTR and that gravity to kind of account for that. You have to basically size it for the full load, plus a little bit some. So looking at a lift station at this point, the total required flow, as I said, was 36 GPM. You always want to be pumping down a lift station, so you apply about a 10%. So I pump about 40 gallons per minute. So this lift station is 120 gallons for 3-minute residency time, and the system is duplex. And this is just one example of a duplex lift station. That's how you would look at sizing a kind of a basic lift station design if your only things coming to are lab sinks. Then if I go through the gravity flow profile, this is where I start to apply my diversity factors. 60 lab sinks, 60 GPM, but really you're probably only going to see like 12 GPM. So if your lift station is going to fill up and then kind of pump down that higher flow rate, but you always want it to do that. You want it to be empty effectively. In this case, you want to kind of size it to be more accurate to what you're going to see 99.9% of the time as far as an actual flow rate. So I have my diversity factor here, 20. Then I assume only 2 glass washers for 16, 5 autoclaves at 10 GPM. So I only have a total gravity flow of about 38 GPM. So I have a lot more fixtures here, but I actually end up with a flow rate very similar or even less than my pump flow rate. And that's just because of how I have to look at them from sort of a different sizing perspective in that case. But when doing that, this is what gives me my total flow. So my total flow is 78 GPM. And my minimum flow is always going to be this 40 GPM. Whatever the lift station is going to run, it's going to run at 40 gallons a minute. So the next step is looking at what the waste profile is. We talked about this a little bit in this conversation, but obviously we're talking about something here really kind of in your standard waste range, about 3 to 11. That's a fairly common waste range to sort of see. Maybe there's some high purity water present. When you get down here into the 2, 1, or 12 or 13 pH ranges, you're going to get a little bit stronger waste streams. That's a bit of a special consideration in those cases. So 78 GPM, 20-minute residency time, 1,560 gallons total, or 2 800-gallon treatment tanks, which is what we'd end up with here. That gives me my full diversity factor. That gives me my full 20-minute residency time across 2 stages for 78 gallons a minute. Perspective, from a size and a P&ID perspective, this is my 2 tanks, acid base. That could be my buffer injection as part of my alkalinity. You can see here, this is your feed coming in, gravity and lift station, your reagent tanks, 2 stages, and then your effluent monitoring in those cases. And it is worth noting you always have to have an effluent monitor for any pH system. It's typically gravity. And you can also people also have lift stations on the effluent of a pH system as well. If you have to pump up into your drain, as opposed to being able to go strictly by gravity in those cases. And you always have to measure pH as part of your effluent. You may have to measure flow. You may have to measure more such as temperature as well, depending upon what your permit is and also what you're dumping down the drain in those cases. Do our last poll question. All right. So when designing a lift station, what diversity factor do you apply? And the question obviously, there's no diversity factor. For a pH system, you typically apply a 20 to 30% diversity factor. Not always. We'll talk about that in a second. But for a lift station, you do always have to apply. You do apply no diversity factor. The reason I say for a pH system, it's typically 20 to 30. If you have a known process stream that dumps, that's just your diversity factor. So if you always have a certain flow, or you always have a certain process or tool that continuously dumps, and obviously then there's no diversity in those cases. Diversity factor comes up when you have more like fixture-based designs going on as part of your pH system. So here I kind of went through a few standard. We're going to kind of wrap up here talking about a few standard products. We're going to show you guys some models and look at some of the custom things that go into these types of systems. But at Burt Process, we do have a number of standard pH system designs, the smallest of which is our PHX model, which you can kind of see illustrated here on the animation. And these run the gamut from a PHX 100 to a PHX 500 with a flow range which varies between about 7 to 33 gallons per minute. And this really helps kind of maintain the residency time. You can see in the model there now, that's the actual chemical injection. There's your agitation as the waste is actually treated. And the real benefit to these style systems is they're very small. These are designed for like laboratory environments, single labs, tenant fit outs, even for small colleges and university applications, and even very small pharma labs as well. And because they run the gamut from being very small and sort of the 2 foot, to basically, 2 foot deep to like 5 feet wide, basically the size of a desk, up to 6x5 essentially. And these can be plugged into an actual wall outlet. And they come with everything you need as part of an overall pH system, from the reagent tanks as well as the treatment tanks, effluent monitoring, agitation. These are what really have come to replace the sort of passive-based systems, and these can be fully integrated into a lift station as well, either feeding to these or they can feed out to them as part of a treatment. So here's kind of a rough breakdown, again, using our assumptions from before. PHX 100 is less than 20 sinks, so PHX 500 is 90 to 110 sinks. So it kind of gives you an idea of how much you can actually put through one of these, relatively small units in these cases. As I said before, as you saw in the animation, this is the look inside. You have the front section here, the treatment tank, top entry where you have your vent, manways, and agitators as well. Moving on from the very small ones, there's also obviously much, much bigger pH systems, and this will refer to as our ACS or short compliance systems. And these are basically integral hybrid batches. So these are flow through with integral hybrid batch design. And these can treat flow rates. Standard ones go up about 300 GPM. Custom ones can go to 2,500 to 3,000 gallons a minute as part of a multi-skid system. And these have that full integration of higher flow through. They have different features in them which will allow them to treat higher strength waste. You see these a lot in the pharmaceutical industry. You see these a fair amount in more industrial, some laboratory settings as well, but these are more food and beverage laboratory, pharmaceutical, semiconductor facilities where you're going to be seeing waste more in that 1 to sort of 13.5 range. They have integral recirculation pumps on them that allow for treatment. A much faster treatment cycle than just having simple drip chemistry, like I showed you earlier, as part of kind of a dual stage design. And these can be fitted with different options, such as, heat exchangers. They can be they can be multi-stage. You can see here, you can have redundant recirculation pumps on here, different materials as well. There's a lot of customization that can go into these sort of standard designs as far as instrumentation, PLCs, SCADA integration. But they still at their core have the basic designs that we talk about as part of a standard pH neutralization system. Here's some different options I just talked about: single, dual stage, diversion or EQ tanks, heat exchangers, um, bulk reagent transfer. They can have CO2 utilized as treatment. They get a lot of different options. And a lot of the information, standard information, is also available on the website for those who want to take a look at it as well. And these are some of the more standard sizes, 50 to say 150 GPM. You can see overall size get a little bit bigger at like 13 feet by 6, up to, some of the larger ones are going to be, almost, 16, 17 feet by 8, which is still a relatively compact design for 180, for 150 GPM system. They're all 460 volt flow. And then you have the little ones, as you can see here, these are some of the examples, the drawings here. The reagent tank for circulation pump, this is your actual treatment system. Then your effluent, where you have basically a dual U-trap configuration, so you have that additional hybrid volume in here. Should you have to go into batch mode, as an option, you can eliminate that and just have it go back to an equalization tank upstream or a lift station as well. And it's just a P&ID on these. That's what I was just referring to here. You have that kind of hybrid batch volume built in here. This is your recirculation loop as well. We do make these on a smaller scale too. It doesn't necessarily imply just because they have more sophisticated control systems, controls and treatment that are not designed for smaller flows. These can go down as far as 10, 15, or even 25 GPM as well. But what you're pretty much using these for is going to be a higher strength waste. So if you're seeing waste that's going to be, in that range, sort of outside of sort of 3 to 11, 4 to 10, you're going to kind of move away from the PHXs and the two-stage system. You're going to look at more of a technology like this. And there's a lot of different custom, just like there is with lift stations. Everything's kind of a customizable standard. You can see here, these are some of the fiberglass treatment tanks I talked about earlier, which are designed for high temperatures. These are just reagent assemblies here, which are designed for like when you have on-site built tanks for higher flow. Two-stage systems, explosion-proof pH systems. In this case, it's actually a batch system. You have your equalization tank, then you have your treatment tank here, and it's all class 1 Div 2 rated. This is where you start kind of getting into very specific applications for clients. And that's really what these are for. It's not a one-size-fits-all. There is kind of a baseline we start with as far as, here's kind of a style, here's the residency time, here's some standards, and then you end up obviously kind of moving into really this arena at this point. We get kind of further down into the design to meet individual clients' needs. And we also do containerized systems. And this came really to the forefront even a little bit before the pandemic, and it came a lot more obviously during as kind of lasted, where you rather than skidding these systems, as you saw, most systems were skid mounted. A lot of what we do today is we build systems right into an actual modular building or modular container. The ACSs, the lift stations, all our different systems. And then we utilize them, they can basically drop right next to a facility. So if you're coming out of your facility with a waste line, you just pump it up into one of these, and then you don't have to impact your system in like any way at that point. You're actually building in, you can see here, this is looking inside. And basically you're going to build the entire system in a modular just like this. This is like HVAC, these can have safety showers in them. They can be retrofitted in the field for fire suppression based systems, high voltage, low voltage, and you have a completely containerized modular system ready to go. And a lot of this kind of started also with sort of mobile clean room applications, and we've worked with a few mobile clean room manufacturers as well to do some applications like this. This is taking a look inside some of the finished ones here. You can see, in addition to the animation down there, this is what they look like. You have, your treatment tanks in the back. This is some of your reagent vessels. This is the actual looking at the treatment tank on the other side. This obviously is showing the full modular at this point. There's different angles. These have all acid resistant or chemical resistant lighting in them, slip floors, containment pans. It's kind of a unique way and kind of a nice way people like to do these where they don't have to then impact or take up precious floor space in a building which is obviously at a premium when it comes to these systems can get pretty large. Some of the bigger pH systems, obviously. And this is one of the turnkey operations that we do offer. There's more information available online. We have a whole video that kind of walks through how a PHX actually operates. If those of you who don't know me, that's actually me in that video right there. And this is all available. And sometimes also be linked to the survey, which comes out at the end. A link to this as well as future webinars. I'm not going to play this right now. And then obviously this is looking at kind of what a bigger system looks like. So this is one that's rated for, about 400 or 500 GPM. You can see they get big, obviously. You can see that's the effluent U-trap there. The mixers. Again, it's just it is a dual stage system. It is a dual ACS style system in this case. It gives you a perspective. This is actually during the testing of these systems. One of the benefits, obviously, of doing a skidded or containerized systems that you can do all that factory wiring, testing, full FATs before the system even ships to the site, and then where you can then do the final startup and all these, all of that as part of these systems, transfer of chemicals, etc. So with that, we have another webinar coming up in October. We'll take a break here in the summer, and we'll actually go really in depth into containerized systems. I kind of sort of touched on that today. But we have about 10 minutes here. If there's any questions.
Hey, Mark, there's one question in the
into the box here,
comments.
but I could ask supplemental questions.
So one of the questions we have here is, I'm not sure I understand why you're saying why you can't use diversity for lift station. And so the reason we don't use diversity for lift stations as much is because when you have a lift station, the difference between a lift station, obviously, and so a gravity flow pH system is a gravity flow pH system. The reason behind that logic is when you have a lift station, you have to assume, because you have a small tank volume, and you have to assume that that's a point where if anything doesn't go through, your only means of leaving that's through the pumps. So if you do for some reason have a spike in flow, you don't really have a lot of volume there to actually retain it. You have some, obviously, you have that 3 to 5 minutes of residency time, but very often those are basically sized for the max flow, because your only option is if that diversity is incorrect in that small situation, you are going to overflow your lift station. In a gravity-based system, what effectively comes up is, if I say size it for 38 GPM and I have 50 for a little bit, it just runs through the gravity line, and you have that CSDR effectively to catch it in those situations. Do you have to always assume a 100%? Not necessarily. In all these situations where if you do have, the flow rate comes out to be very high. In the example I showed, it was a relatively simplistic one. There is a little bit of kind of give and take in that. If you obviously can end up with a very high flow rate in those situations, then you may end up with a situation where you'd have somewhere close to, maybe like a 70% diversity factor. So you're going to kind of cut it down a little bit, but not to the same level where you'd say, hey, my worst case flow rate is like 5 gallons a minute. Where they could have 25 gallons a minute as an example. There's some different schools of thought, obviously, on that. The sizing I'm giving here is probably a little bit more sort of conservative in those cases. We have another question here, and this one actually comes up quite a bit, which is, when you talk about lift stations, how low can you actually make an invert to a lift station? So a little bit of context for this. I kind of understand where this question is coming from. I know the person's asking it. If you have a device, say you have a semiconductor tool, or you have you have an autoclave or a glass washer, your invert could be like a foot off the ground. And obviously, in a lot of examples I showed you, you have these lift stations which look relatively tall in some cases. And there are different designs. So a lot of standard lift stations utilize a top vertical mounted pump. And when you do that, you only have a certain impeller depth, which can be anywhere between, if it was a non-bearing style pump, about 11 inches. If it's a bearing style pump, it could be considerably lower. But for a lot of smaller designs, a bearing pump just isn't practical in those cases. So most people will say if you're using kind of a standard vertical pump, you need to be about 10 inches from the rim. That being said, if you have to be lower, you can get as low in the tank as you need to be within about 3 or 4 inches of the bottom of the tank as a fill if needed. The only thing you have to do in that case is you need to have a different style of pump. You need a kind of a cell priming pump, or you need to have more of an in-tank submersible pump in order to allow you to actually pump at that point, because your impeller has to be submerged to allow a lift station to actually operate. So in that case, what can end up happening is you can end up with a lift station that can get really short. Um, and there is a geometric limit to how small you can actually make a lift station, just based on getting a pump, a level control, and everything in there. That tends to be about 5 to 7 gallons. The problem is when you end up with a flow, say 15 GPM, that's a very small lift station, a very small volume. Specifically, you have a pump in the tank to achieve that. So that's where you get a little bit of some design on that. And we do have models which are actually designed to operate in those situations. Just to kind of follow up on a reverse of that, there's another way to look at this whereby you have, a line coming that needs to be pumped to a pH system. That line's 7 feet underground, or you're basically below grade. And then you have the trade-off conversation, which you could do both ways, which is, do you put a lift station in fitting on the cover, and then your pumps are 7 feet below grade, or do you put the pumps on a skid above the grade, which is the tank down there, and you have a self-priming design, or do you do you actually increase the tank height all the way up, and then you have a side inlet fitting? And I've done all three different ways. And that's where you kind of get into some of the nuances of kind of lift station designs, is where you have to look at what those inverts are, what your flow rates are, what those volume is. Because you also don't want to go too deep. Because now excavating is very expensive in those cases. So this line's 7 feet deep and it's 200 gallons a minute, and I need to put 1,000-gallon tank and go 7 feet deeper. That's not a very practical solution at that point. That's where you kind of get a lot of the sort of engineering that can be done. And there's a lot of different solutions to kind of solve some of those different issues. One of the other questions we have here is, what would you recommend as far as the difference between using onboard reagent tanks or using chemical drums as part of a pH neutralization system? I get this question actually quite a bit, and the answer is it's really an owner preference in those cases. There's no way to put chemical into a pH system without some form of chemical handling. If you have onboard reagent tanks, you have to fill them, so you have to bring a drum or have a bulk storage, and then have a way to actually pump it into your tanks. If you're using drums, you're gonna have a suction one that you have to then remove from the empty drum. It's gonna have a check valve. It's gonna have some form of chemical on the outside of it as well as in it. Then put it into a new drum. It really comes down to preference. I think having chemical tanks is cleaner than wheeling up fresh drums and having like a spill pallet below it. But again, that's kind of based on sort of my own preferences, in those cases. A question here: what's the largest flow rate system that can go into a containerized design? So we're talking about a container. You're talking about containers. Most of them are based on standard Connex box design, which means you have an 8 by basically 40 feet as your maximum length. They do make specialty ones which are about 50 feet in length. And you can get a high Connex box, which is over 9 feet. And a lot of times we do use the taller Connex boxes that go up to about 9 feet in length. 9 feet in height, I apologize. About the biggest you can do in a containerized system, a single containerized system, is about 200 gallons a minute. And that's because even though you have this large area, say 8 by 40, which if it was a skidded design, obviously that's a very big system. When you're talking about a containerized system, you need to have all that access in that same area. So your actual sizing and your actual area in a containerized system is actually not that big, because you have all different walkways, access, environmental controls all built into your system. So you actually have a much smaller footprint than the true sort of 80 by 40 feet in those cases. All right, it's been an hour now, everyone. So we're going to stop. If there's any additional questions, my contact information is available, and everyone feel free to reach out. Again, we'll be sending out a survey as well as some additional follow-up information as well. I want to thank everyone for joining us. Everybody have a great summer, and hopefully I'll see all of you guys in October for the containerized system, and we'll go into some in-depth about that. Thank you.